Okay, I have started the recording. So let's wait for 2 more minutes that other people join, and then I'll start. Okay, let's start with today's session. So this week, the topics were pretty easy. So I have um, made a PPT on the previous year questions. So we will discuss the previous year questions. But before that, I want to recap all the topics that has been covered in week 3 lectures. Additionally, I have one quiz as well prepared for you guys. It's a very fun quiz. So I can present the question as not much student is attending it. So whoever will be watching the video in YouTube, they can attend the quiz and they can see what the answers are and things like that. So let's start the class. So this class was based on mainly the tool path planning of additive manufacturing technique, and then the liquid-based additive manufacturing, such as the first classification under ASTM, which is that photopolymerization, has been started. So uh, let's go. So under tool path planning, so first of all, why tool path planning is important? Because when we print it, we print layer by layer. So here we are talking about how the layers will be defined. So in the previous lecture, if you remember, we have talked about the slicing, the STL file format. So in STL, we are saving it in a .stl, which is triangulation of the whole surface, and then we are cutting the planes out of it. So we are making the slices, which is the layers of printing. But if I talk about single layer, then that is also important how you're printing single layer. And that process needs to be multiplied by 500, 600 to get the whole geometry. So each layer printing is very important. For example, if we are printing it in directed energy deposition process, or we are printing it in laser powder bed fusion process, or we are printing it in fused deposition modeling, the tool path planning will be different for different processes. Because each layer history will be different for each processes, because the by layer history I mean the heat, the thermal history, the tool path, like how the tool will move, because Each tool will be different for different processes. For example, in FDM, fused deposition modeling, it's just a nozzle from which the semi-melted plastic filament or semi-melted metal filament is coming out. But in case of VAT photopolymerization technique, it's the liquid resin. So under VAT photopolymerization, there are many processes. But for example, for SLA, there will be laser beam, which will just cure the resin layer, each layer. So here the tool is some arrangement of lenses through which the laser is coming. In DD, directed energy deposition, in from the tool, which is the nozzle or the cladding head, the powder and the laser both will come at the same time. Whereas in LPBF, only the laser will coming from the galvo scanner and F theta lens. So the tool is different for each processes. So that's why the tool path will be different for each process. Now, uh, how the tool path will be defined is based on how your geometry is. Now, in case of tool path, there are two steps. One is the area filling. The second one is the contour. So area filling means the whole layer. So if the okay, if the layer looks like this, where there is a hole inside, then this is the field area. Like this, the area needs to be filled with the material. So if it's laser, only laser, in case of LPBF, the laser will scan this whole
Ma'am,
area very
ma'am,
fast. Yes. Yes.
your screen, are you writing or it is not visible
Okay,
actually?
it's not shared. Sorry, sorry.
Ah,
Yeah. Screen, I forgot to present. Is it visible now?
now it's visible.
Okay, so if your geometry, if your single layer looks like this, and this is the hole inside, then this is the part to be filled. This is the area to be filled. If it's LPBF, then the laser will move like this to scan, like to melt and solidify the whole area. It's not perfect. I'm drawing it with the mouse. So this is the way the tool of LPBF will move. And it will not move at the middle because there is a hole. And there are two parts in it. One is the area filling. The second one is the contour. Contour means I'm talking about the outer periphery of the geometry. So because if you are printing it, if you are printing one layer and if you are printing it in FDM, the wire will move like this, something like this, and you can see the layer, the wire, how it got deposited even after printing. It will something look like this. So this is the geometry. So that's why in some cases, after printing, after depositing in the layer, the tool will also move in the periphery to deposit another line in the periphery to define the periphery. So that in the periphery, there will be no porosity, there will be less surface roughness, and the layer will be defined, nicely defined. So that's why there is two steps. One is the layer filling, another one is the periphery contour scanning. So the periphery one, we call it as contour scanning. In case of laser, there are different names for different processes. So now, if I go by slide by slide, so first is the contours, like the area filling. So the area filling can take place in various manners. So it can happen that first the periphery is drawn, like the periphery is deposited, and then the area is deposited. The other way it can also be there, like first the area will be filled and then the periphery will be deposited. It depends again from process to process. So I can give you one example. In case of laser powder bed fusion, when we print each layer, if my layer looks like this, so the laser will generally feel the area first, like it will feel the area first in some manner. And when the area is filled, it will scan the periphery and remelt the periphery again to deposit. Why? Because in case of LPBF, the laser is melting the metal. So because of the melting of the powder particles after solidification, there will be expansion. And because of this expansion, the layer will have some problem in the periphery. And also, as there will be powder bed over which the laser is moving and melting, at the periphery, there will be a lot of unfused powder particles which are connected with the geometry. So to avoid the surface roughness and porosity due to this reason, the laser will rescan the periphery again to remelt the periphery and make it more defined, as a result of which the unfused powder particles will be remelted and will be fused together, and the porosity will decrease and the surface roughness will decrease. So this is the reason of contour scanning in LPVF. Similarly, in FDM, generally the periphery will be deposited first and then the layer, then the area. So the reason behind this is there the material itself is coming. So in our childhood, when we used to draw something at the age of 3 or 4, we used to define the periphery of the geometry first with the color, if you remember, and then we used to fill it. The same concept, just to make sure the periphery is defined, the geometry is defined. So so in FDM kind of process, the material will be deposited in the contour first, and then it will start scanning the area, or it will start feeling the area. So in case of FDM like process, it may happen that as the material is getting deposited, and there the material is semi-melted and deposited, it's a wire kind of material, so it will be very thin. So it will be like 400, 500 micron width of the wire which is getting deposited over the well plate. So it may happen that 2 to 3 lines of contour scanning will take place. So basically, the FDM will do this thing thrice. It will again scan it's not very good. Just try to understand the concept. It will do this thrice, and then it will start to feel the area. This is the process of area filling and boundary scanning. And how this thing will take place is basically coming under the toolpath planning. So area filling method can be 2D surface, 3D surface. In 3D surface, it can be grid cutting, pixel, mask, and path. So, or in 2D surface also. But if we are talking about layer, then it's 2D geometry, but obviously the layer is 3D because it has some thickness. So let's see how it can take place. So requirement of area filling methods. So it is needed for quick heat dissipation, minimum number of lift, constant machine feed rate, constant step over. So basically it means that when you are choosing an additive manufacturing process, you have to be sure about how the tool path needs to be planned. The tool path planning will not be same for each process. It depends how the thermal gradient will be there, what is the thermal history of the process. Depending upon that, you have to define the area filling or tool path planning, what I have described here, that in LPVF and FDM. Same thing. So grid cutting is basically in case of loam, laminated object manufacturing or sheet lamination process. The process takes place like the paper sheet will come, and if this is your geometry to be built, so there will be a knife which will try to cut this geometry out of the paper, and also this is not a part, so this will be cut as well. But if the knife moves like this and cut, there can be some problem. So instead, what it does is it cuts the excess portion of the paper by grid by grid. so that it will be more defined, a more controlled process, and like that you can get the geometry. And when the next sheet comes over it, it will again cut the unused portion, and a roller will move from this side to this side onto it, so that the heat and the pressing of the roller can join these two sheets, and this process will repeat itself to get the final geometry. So this is one example of grid cutting.
Ma'am, can
Now
you
pick,
explain once more? Didn't get
yes, yes. So in sheet lamination process, there will be a sheet of paper which will come onto the bill plate. If this is the geometry needs to be printed over it, so there will be a knife which will cut the paper like this. So my mouse pointer right now is a knife. It will cut the sheet like this. Okay. It will be systematic. Then in y direction also it will cut till end. I'm not going till end, so it will cut till end. So the unused portion, which is not necessary for my printing, this portion of the paper I don't need because this is the geometry. So I did not need this portion. So it will cut the paper in this portion so that this geometry will be intact. And this is my first layer. When it is cut, another paper will come onto it, another full paper. Again, the knife will try to cut this grid so that this portion will be intact. Now imagine I have two papers from which this geometry is intact in both the paper. Now there will be a roller. This roller will roll over this surface. So the roller, when it's rolling over the surface, there will be the pressing of the roller, and due to the rolling, there will be some heat also. The roller is heated roller. So because of the heat and the pressing, these two papers will be fused together. This portion.
Okay, the
Other
place which
portion
is
will be
intact.
fused as well. Other portion will also be fused as well. But other portion has these cuts as well. So after 500 layers, for example, this process is repeating. You have a bunch, like you will have a box like this, which box is fully made of paper, right? But from the box, this portion is intact because this is my geometry, and all other portions have this grid cutting. So if now you take a knife and manually start uh, just separating this grid cutted portion, you will get the intact geometry, this thing, and this will go like few cubes of paper will come out of it. Do you understand now?
Yeah, the intact portion will come out separately, isn't it, ma'am?
Yeah.
Okay.
It will be little bit fused with this grid cut portion as well. But if you
Okay.
start separating it manually with a knife, it will come out. So that is
Okay.
also a process by which you post process the final geometry produced by laminated object manufacturing. In
So
one
does
of the
this
lectures,
okay. Does this
you will
rolling help
learn.
in cutting easily?
The rolling is there just to press two papers,
Okay.
so that two papers will be glued together. So you can say it's not a normal paper. In some of the laminated object manufacturing process, there will be a glue also, which will be spread over the portion where the geometry needs to be printed. So maybe in this portion, there will be the glue dot drop of glues coming, and then the next paper will come. So that is also one option of loam process. So in this process, the tool path planning is basically this grid cutting. The tool is cutting the paper into small grids. So this is the method of grid cutting in laminated object manufacturing, which you cannot find in any other processes. So that's why this tool path planning is very separate from process to process. Then comes your pixels. So pixel is another method of area filling. So what will happen? So in DLP based process, so it's a wet photopolymerization technique where I did have a slide last class, if you remember, that there was this resin onto which there will be a vat of resin. Vat means a container, nothing else. There will be a vat of resin, a container full of resin, and there will be a bill plate, which is mounted on a lead screw. This is the lead screw, and this is the bill plate. So, this bill plate, and there is a screen from which the UV light is coming. So, this screen is actually placed here, just below the vat. So, now the UV light is coming. So, the screen is looking like this. This is the front view of the machine. This is UV light. And this is the top view of the machine. From top, you are seeing the screen. Onto the screen, there is this vat full of liquid. And over the vat full of liquid, you have placed your bill plate. So your bill plate is basically now, if I zoom the view, then it's something like this is my bill plate. This is my vat full of resin. And there is one layer thickness resin present below the bill plate. And all other portion is also covered by the resin. I think this point is clear. This bill plate is attached here. So this bill plate can move up and down. Now the bill plate position is in such a way that the bill plate and there is the screen. This is the screen. So this screen and the bill plate is having one layer thickness gap in between. So now my bill plate has one layer thickness resin. Now, if my geometry is looking like this and the screen is having this many pixels, so these small squares are called pixels. So in our mobile phone, when we take the photo is saved in pixel format. So in some of the phones where the camera quality is not good, if you zoom the picture, if you zoom a lot, you will see the picture will be segregated into pixels. The picture quality is degrade, we say it. So basically, the pixels are not very small, because of which when we are zooming the picture is giving us that pixel by pixel view. That's why we are saying the quality is not good. So now this screen is also having some pixel. This is an LED screen or LCD screen, the same screen that we have in our mobile phone. So now if my geometry is looking like this and the UV light is coming in all over the screen will activate its pixels only in that position where the geometry needs to be printed. So this is what it means. Again, I'm repeating. This is the bill plate. This is the top view. So in top view, if this is my bill plate and this is my geometry needs to be printed, then these will be the pixels which will be activated, and that means the UV light will reach the resin in this activated pixels only. So the UV light is actually coming in throughout in all over the screen, but the screen is not allowing the UV light to reach the bill plate. And in the bill plate, there is one layer thickness resin. So that means when finally the UV light is reaching the bill plate, the resin will be cured in that position where the UV light is reaching. And it's taking place by pixel format. So this is the example of area filling method.
Is it
Yes.
build plate or build plate?
Build plate. Yes, build plate.
Okay, so only a portion of the build plate needs to be activated, right, ma'am?
not bill plate. So there is two things. There is a screen. This is the screen.
Okay.
On top of the screen, there is a vat.
Yeah.
Vat means a container. Now the container, the bottom surface of the container is transparent to UV light. Okay.
Okay.
And inside the container, the bill plate is there. So if now you give the UV light, the UV
Mm.
light should reach the whole bill plate, the whole resin. But now you have placed a screen in between, and in the screen, the pixels are activated in this portion. So only
Mm.
in this portion, the UV light is reaching the bill plate. Is it clear?
Okay. So the red color that you have shown is the area in the screen.
Yes, yes.
Okay.
This is the area in the screen. So
That is activated
ultimately,
by UV light.
yes, yes. So basically, the screen is having the pixels and it has some electrical connections. So when we feed the geometry in the machine, the screen knows in which layer how many pixels need to be activated. And it is activated means through that pixel, the UV light is coming to the build plate. The
Okay.
UV light is there. This is the UV
Okay.
light.
Okay.
It's reaching the whole screen, but the screen is not allowing the UV light to come and reach the build plate.
Okay.
Yeah. So this is the process of DLP. So now this is
Okay.
the area filling method of pixel. Now you can understand from this picture, the smaller the pixel will be, the better your resolution will be because it's squares. So obviously, if you
Yeah.
need better resolution of your geometry, then the pixels needs to be very, very small. So generally, the pixels are few nanometer or few micrometer, because of which the DLP processed parts are generally very nice resolution parts. It will have a very, very high resolution because of this pixel method. Similarly, if your mobile phone is having very high quality, that means your pixels are very small, because of which whenever you zoom the picture still is nice. It's not breaking into pixels. It's not segregating the pixels. So its quality is good when the pixel number size of the pixel is very small. Now the area filling method using mask. So in some VAT photopolymerization technique, the mask method is used. So now what is this mask method? So basically now there will be this glass with no mask, and this is the geometry needs to be printed. This is not printing, this is build plate. Okay, this black portion is build plate, for example. And on the build plate, this is the layer you are printing. So you will be using a mask. Mask is nothing but a material which is not transparent to UV light. So if you place the mask onto the build plate, onto the resin, and now you expose the UV light in throughout in the whole build plate, so only where the mask is not present. So here the mask is not present. So the resin will be cured in this portion. Cured means it will be solidified. And in this portion, it will not be solidified. So this is the process of masking. So for each layer, there will be a mask. So when the first type of additive manufacturing came, it was wet photopolymerization. And it was this type of additive manufacturing where people used to produce masks for each layer, and they will put the mask onto it and let the UV light come and reach the whole resin. And as the mask is placed at the mask, the UV light is not reaching the resin because it's not transparent to UV light. So the UV light is curing the resin on this position. So this is a very, very rigorous method. People don't use it these days, but this is also a technique in area filling method.
So the mask is the black region or white?
Black region. It's not a black region. It's basically a, suppose a paper which is not transparent to UV light, and you have placed the paper onto the resin, and the paper is looking like this. That it has a cut here. So mask is same. This black is the mask, and this is the part. So when you just remove the mask after curing, your part is ready. Your layer is ready. This is one layer
Okay.
where the resin is cured.
Okay.
This white portion is build plate again, and this is the
Okay.
cured part.
Okay. The
Okay?
portion where mask is there, it won't get cured.
Yes,
Resin won't get
yes,
cured. Okay.
yes. So now comes the raster. So raster is a thing that you need to learn, because raster is a pattern that is used in all advanced additive manufacturing technique. Raster means a path that the tool is moving. In all the cases, we were using a third party. So in grid cutting, the tool was moving to cut the grids, right? Here the tool was moving. But in this, there is a third party with like a third element which is working here. Here, this screen is the third element which is working, which is having the pixel activation thing. Here, the mask is the third element that you're just putting onto it so that the UV light can come and cure. The UV light actually the energy source. Here, the UV light is the energy source. Here, the roller, the heated roller is the energy source. But in some additive manufacturing process like DED and LPBF, you cannot use a mask, or you cannot use the pixel. You have to move the tool itself, just like what was happening in this process, laminated object manufacturing. The tool itself was moving like this to cut the grids. Similarly, raster works like that. So in case of raster, the tool moves in defined paths to deposit the material. For example, if this is the nozzle, through the nozzle, the wire is coming, the semi melted wire is coming. What happens in fuse deposition model? So if the wire is coming from here, and if this uh, tool is moving in this manner, so it's going there, this dotted line is where the tool is moving to its next position, but it's off. The wire is not deposited in this red. These black lines are the deposited lines. These red dotted lines are not the deposited lines. It's just how the tool is coming back to its next position. So here the tool will, the head will deposit the wire, then it will come back, then again it will deposit, then again it will come back, it will deposit. This is how it works. So raster means, raster path pattern is simple, efficient, and robust to copy with boundaries. However, the build accuracy is poor in the layer, because if you are using it for FDM process, for example, in FDM, the layers, each layer will have this raster patterns which are visible even after printing, because of which the layer roughness is not good. No, like the layer is rough. The part is rough. It has surface roughness. It will have some porosity. The geometry is not that much defined. The surface is not that much smooth. This process is like pixel. It will give you very smooth surface because the size of the pixel is very, very small. But in these processes, you cannot minimize the size of the deposited bead to some extent. And because of which there will be some limitation in terms of the accuracy of the layer. And as I said, in raster, there can be multiple way of rastering. So this is one way where these three are same geometry. You can see 1, 2, and 3 are same geometry, but the rastering pattern is different. So here it's just moving in S direction. and depositing. Here, the tool is moving in Y direction and depositing. Here, it's first moving in X and then it's moving in Y direction. So it's X rastering means all the layer will look like this. It's Y rastering means all the layers will look like this. But it's XY rastering means it can happen that the first layer is looking like this and the second layer is looking like this. So the third layer will again Y rastering and the fourth layer will again be X rastering. The fifth layer will be again Y rastering and the sixth layer will be again X rastering. Like alternatively, it's doing. So now, what is the reason of these many rastering options? Because in pixel, there was only one option. The pixels will be activated and it will be cured. In mask, you just cut the mask in this shape, put it, and it's done. In case of grid cutting, the tool will move and cut the grids. The grids, the pixel of the grid, like this small squares are, sorry, the small squares are same in length and width. So it's simple. But here we have already shown you three different patterns. Why is it so? So just imagine when the whole part is printed like this, and after that, if you do some mechanical testing of this part, for example, tensile testing. So if you just tensile test this part in this direction, means if you pull this part in this direction, and if you pull this part in this direction, the result will be different because the property in X direction and Y direction of this part will be different. The strength of the part in X and Y direction will be different because it's very directional deposition. The deposition is very much directional. You are just depositing it in one direction. The porosity in this gaps, like in between two lines, will be very high. If you do this, it's same. If you just rastering in one direction. But if you do this one, third one, then you are alternatively doing it. So ultimately, when you will do the tensile testing of this part in this direction or in this direction, the property will be to some extent same. So we are achieving isotropy in the part. Isotropic properties are very important because we are printing it not for prototyping anymore. We are printing real parts. So when we are talking about real parts, it also include the property of the part to be printed. Property means the mechanical property, the microstructural property, the tribological property, corrosion property, etc., etc. If it's metal. If it's plastic, then obviously the strength, the mechanical property, etc. So if you are talking about the mechanical property, then it should not have different property in different direction. So basically, the strength of the part in X and Y direction should not be different. If it's different, then it's called anisotropic, which is not needed, which is not good. So if it's better when you achieve isotropic property. So that's why this XY rastering is better. Now again, in this case also, when your layer is in this direction, you are only going like this. So this strength will be different than X and Y. And this strength will be different. Like this diagonal strength again will be different because all your layer is going towards X plus, like Y plus, and all your layers are going towards X plus. So there is no layer which is going in X minus and Y minus. So that's why comes the zigzag pattern. So zigzag pattern means it can be like in rastering pattern when you do this. This is my X rastering and in the next layer, it will be my Y rastering. This is called the XY rastering with zigzag pattern. In this case, if you see each layer, if I talk about this first layer, then in first layer, itself, it is having isotropic property because all the deposition is not towards one direction. It's in opposite, alternative directions. And if I talk about the second layer, then in second layer,
Hello.
sorry, my network was gone in between. So I'm sharing my screen again. Is it visible?
Yes, ma'am.
Yes. So if this is my first layer and if this is my second layer, so in each layer now I have the alternative directional layer track deposition. So this one line is called track and this whole thing is called a layer. And then layer by layer, we are depositing the product. So now, as I have some alternative track deposition also, so my properties, like mechanical properties, will be even better in this case. So it will be more isotropic, which is required. So that's why in rastering, XY rastering is better, and then comes the zigzag pattern, which is again better. Now comes the contour part. So in area filling method, where the tool is moving, there is another technique which is called the contour path. So you can see the video, you can see the image, and you can understand how this contour is moving. So if this is my tool, it will start scanning the layer like this, and then with the contour size will be decreased, and slowly it will go till the center of the part. So these are the contours by which it's depositing. Similarly, for this part, as this part was kind of identical, what do you call it? Like it's same from both the axes. So this part is not like that. So that's why it will start scanning the contour. And as this part is different than this, these are not identical. So it will scan the contour differently than this part. So this is how the contour path tool will work.
Ma'am, this contour
The
means boundary. Or
boundary. So It's not only boundary, but how we are scanning the boundary here, the same thing will be replicated for the whole geometry just by reducing the size of the boundary. You see the lines? These lines are basically the deposited lines. It's
Yeah.
scanning the boundary and it's reducing the size of the boundary to reach the center of the part. It's called the contour part. So basically, the contour is mimicked for the whole part, for the whole scan layer, and its dimension is decreasing till when it reaches the center. Then comes the spiral. Spiral is different than the contour. Why? Because if you see this geometry very carefully, then you will see this is one contour, this is another contour, this is another contour, right? You can see this is one contour, this is one contour. These contours are not connected to each other. So that means the tool needs to be start and off, like turn on and turn off. There will be how many contours are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Almost 23 contours are there. So that means to print this simple geometry, the head or the system or the tool needs to have 23 times of on and 23 times of off. Each turning on and off will take some current, and each turning on and off will have some inertia as well. If it's a tool, then and if it's moving like this, so when you're turning it off, there will be an inertia. And because of the inertia, there can be a little extra deposition at that point. If the point is moving like this and if you're turning off, it may does this. Okay, it's too much zoom. So that means your machine will have lot of turn on and turn off, which is not good for the inertia and for the quality of the job, and also it will take more current. So in that case, if you can print it like this contour for this part, but there will be connection with each and other contour, so that my laser or my head will not have any turn on and off in between. It will turn on and it will turn off when the whole layer is done. Then it's better. Because if for this part, if there are 500 layers of printing and each layer is taking 23 turning on and 23 turning off, then there will be 500 into 23 number of turn on and turn offs for this part to be printed, which is ridiculous. Because of which people invented this spiral. So in
And
this
how
process,
come?
sorry, can you repeat your question?
How does 23 into 500 come?
So if this part has 500 layers and each layer is taking 23 turn on and 23 turn off, then you will have 500 into 23 number of turning on for the whole part.
Okay, so for this 23 turn is for one layer, right?
Hmm.
Okay.
This is one layer and the tool is moving like this. So to reduce that thing, because it's ultimately CNC controlled, and if you're putting so much turn on and off, it will take a lot of current, it will have its inertia, it may distort some geometry, it may distort some accuracy of the part. So it's better to have one way, one go turn on and off for each layer. So if it's 500 layer, already you have to turn on and turn off the tool or the laser 500 times for 500 layers. So it's better to go one way, in one go. So that's why spiral. So in spiral, if this is my circular geometry, so it may go like this. So it may go like this this, and it will turn off when the whole geometry is scanned. Do you remember? Do you understand this spiral thing? It's the same like contour, but it's not turning off. It goes
This
like
is
this.
connected.
Yeah, connected. So it's just
Okay.
like if you're placing a rope like this, so the rope will not have its end. You will just place it like this in a roll, and it will have its end at the end of the part, and it will have it starting here. So this is how the tool will move, or this is how the laser will move in case of different processes. Now comes the space filling. So this process is also a area filling method. Now there is something called the space filling path. So it's called the Hilbert path. Hilbert is basically, if this is my geometry, this is the geometry. This pink line, if you see, this is the periphery of the geometry. This periphery of the geometry, this so let me tell you the thing. So this is called the Hilbert pattern. If you see it carefully, there is only one starting and there will be only one end. So this is the end and this is the starting. If I zoom the picture, this is the starting, and it goes like this, and it goes like this to cover the whole path, and then it ends here. This area filling technique is called space filling path by Hilbert path, and thus you can have only one turn on and turn off. But at the same time, if you are placing a random geometry like this pink line, then whatever is coming inside the pink line, that Hilbert path will be followed to print this layer using Hilbert path. So here also there will be a lot of turning on and turning off. If you now see this picture carefully, this Hilbert path and this portion is just subtracted from each other, and now you get the layer here, and this layer will have lot of turn on and turn off because the Hilbert path is ending here. It's not continuous in this geometry. I- Do you understand this point? If you subtract this part, this layer or this contour from this Hilbert geometry, you get this. Is it good to understand?
So whenever the path touches the boundary of this geometry, it will turn off, right?
Yeah,
So
yeah, yeah, yeah. So it can be like you can try to make the Hilbert in between, then you'll not have any turn on and off. But it works like this. It will make a Hilbert in the square region, and whatever your part looks like, it will just try to take that part. It will subtract the whole Hilbert from your layer, and it will have this space filling technique. But there is also a lot of turn on and turn off technique. So then comes the mat. Now, mat is basically, in case of contour, you were repeating the same contour of the geometry for the whole geometry. So you were repeating the contour to feel the whole geometry. You were not changing the contour pattern for the whole geometry. If you see here also, here you are repeating this only for the whole layer to cover. Here, you are doing the same thing, but you are not having any turn on and turn off for a whole layer. It's same. But for this thing, you first try to make different contour for different region. So for this, you are not going like this. So for this, you have a different contour. For this, you have only line. For this, you have only line. For this, you have line with separated lines. Here it has some corner. Here again it has some spirals. So this is also kind of space. This is also kind of spiral technique, but it has different space filling path for different part of the layer. The whole layer will not mimic the contour. Do you understand this? This it's a little bit different to tell, but if you see this picture, I can show you zooming out. So this part, in case if it was um, spiral path of, or this were the contour path, then it could have been like this. This could have been the contour for this part to be printed, right? If it were a spiral and contour path. This much you remember already. This much you understand already. But as it's a different area filling method, which is called matte, it has different contour in this portion so that you can have better accuracy for the part. This part has different contour and this part has different contour. Again, this part has different contour. But it's all about the contours only, and it has lot of start and off, on and off to make it more accurate, because this is like, this portion is more curvy, so it needs more attention, but this portion is like a flat portion, so it doesn't need more attention, so you can just print the parallel contour lines to fill this area. So that's why they have chosen the contour lines to fill this area, but this has a curve. So to define the curve more accurately, they have printed this contour curve lines to fill this portion. Again, this has a different curve shape. So that's why they have taken different curve contour to fill this portion, and this portion again is different. So that is called the matte area filling method. Then comes the hybrid path. So till this point, if you see this part carefully, each contour is ending. Ah, it's too much zoom, I think. Let it come. Just a second. Yeah. If you see this part carefully, then the contours are ending at the periphery abruptly. It doesn't have any periphery or boundary scanning. The boundary will have some ending. At the boundary, the contour lines are having its ends. So at the boundary, it will look like this. It is defined, it's good, but at the time of, if we are measuring the surface roughness or porosity, it will have more porosity. It will be not that much defined. It will have some surface roughness. So instead, for area filling, what we can do is we can do hybrid paths. So first we can do the contour scanning for the periphery. So for contour, we can do the contour scanning was something like this for the whole part. But instead of the whole part, what we can do is we can do it for 3 layers. And for the rest of the part, we can do just the zigzag or the XY raster scanning. So that's why it's called the hybrid path. And this is the more used uh, way of filling the area in any additive manufacturing technique. If you remember, then I have already told you in my second slide itself that in LPBF, first we fill the area and then we do the boundary scanning. In case of FDM, first we do the boundary scanning and then we fill the area. So both the thing is coming under hybrid path. So this is the concept of different area scanning methods. Now again, this is called continuous path. So here it's like first the boundary and then the raster. So it will again have some on and off. So to avoid that on and off, here what people are doing is they are first selecting the part in different region. So I am dividing the part in different region, and different region I am doing the hybrid scanning separately, but it will not have any on and off. So if you see, this is a very complicated scan or layer. It's an India map. So here we are having the start and here we are having the end. So it has covered the whole area by Hilbert scanning, but the path is continuous and it is having only one on and off. So anyway, whatever our area scanning method will be, we will always try to have only one and off, only one on and off for the whole layer to optimize the power consumption, the to maintain the accuracy of the part, to have a controlled building process. So this is again a much higher hybrid because it has raster, it has contour path, also it has some selection of region to have different contour and raster scan. So
Ma'am, does
this is,
the does this have a single starting and ending
yes, it
continuous?
has a single starting and ending. If I try to find the starting, uh, I can't find the starting, but if you see the lines, you will observe that it has only one start and end. It's going like this, then coming here, then again it's going like this, then it's going like this, then again scanning here, then go here, then scanning here. So it has only one on and off. But again,
All these
it
three.
has
All these three.
all these three. Yes. That's why it's called continuous path. Okay. So the next thing is on area filling method by topology optimization. Now, these are the method that I have talked about are some area filling methods where you have considered that if my geometry looks like this, all my layers look like this, so you are filling the whole area to have a 100% density part. Do you agree with this point that if my part look like this and if I'm scanning all the area like this, it will be a 100% density part or towards 100% density part? Yes.
But the middle portion is not
Yeah,
rendered.
it's this is not a part of the model that I'm printing. It's a
Okay.
hollow part only. Yeah.
Okay.
So it will be a 100% density part. Or 100% is never possible. So it will be 99% density part. So it's a highly dense part. But in some cases, for example, it's very common in case of metal or plastic 3D printing both that people don't print with 100% density. Your part should have a 100% density in terms of your layers. Like your layers should not have any porosity. Your layers should not have any high surface roughness. But if you still want to reduce the weight of the part, you can do the topology optimization. So I'll repeat this thing. For example, you are building a cube, a simple cube, nothing else. So this cube will weigh like 200 grams after printing, for example. But this cube, I can make it at 50 gram as well. That means here its density was 100%. 100% rho means density. But here the density is, I think, 25%. So that also you can do. So now you can question that why do I need to print 25% density? Because sometimes you need to make your part lighter. It can have different application. So first is, if you're printing some, a very hi-fi application is when you're printing the bones or implants for medical purpose. So people do not print 100% dense bone parts because you are printing it with steel. Steel is very heavy. If you put a 100% dense steel in your body, you can't even bear your own the load of your own bone. So that in that case, you have to print it lighter. So to make it lighter, you need topology optimization. Then if you are printing a cube in FDM process, then just to show the cube, the accuracy of the cube and everything, you do not have to print it with 100% density. You can put some gap in between inside the cube so that the cube will be lighter. So my benefit will be I will save material and I'll save cost. I will save time as well. So I am saving all three things together. So why not to print less density cubes when it's my cube is not going to serve any purpose? Or even in some cases, you'll see rather than a fully dense part, some part with 25% density will have better strength because the way I have put the gaps in between the layer is in such a way that the strength or the load bearing capacity has got increased. How? So these all things take place by topology optimization. So this is the example of topology optimization. Means now let's come to one point which is called the lattice. There is something called lattice structure. If you know what lattice structure is, it's good. But if you don't know, then the simplest example is honeycomb structure that you see in the honeybee, their shell. That is the honeycomb structure. So what the honeybee makes for their house, that is the honeycomb structure inside. So this is how it looks like. So if you print the cube with the wall thickness, for example, this cube is having 100 length, and in that cube you have printed this wall with 5 millimeter wall thickness. So your wall thickness is 5 millimeters. So from outside, your cube is looking like a dense cube. But inside that, if you put this honeycomb structure, and this each honeycomb structure is having some wall width, and the white portion is actually empty. This black portion is where you have deposited the material, but it's not this much thin. It has some width. Maybe the wall width is 500 micron. Then you can save a lot of material. You can save a lot of time, lot of material, and lot of cost. So you can reduce the weight by 25% or even 10%. You can print 10% dense part. Your cube will look as it is from outside, but from inside, it's this lattice structures. So one example is this honeycomb structure. These are the different lattice structures you can see. I also have some lattice structures here, and these are the other lattice structures that you can see from these pictures. So these are not random. These have different purposes. They serve for different applications. Some of them will have better strength than 100% dense parts. So that's why topology optimization is very, very important. And this is also a area filling method. Area filling method for 3D structures. So now we were talking about the single layer, but in case of uh, the whole geometry, it need not to have same filling method for each layer. It can have different structure in different layers. layers, and depending upon that, you can change the filling method. For example, this method is very simple. So when your layer is having a fully dense, I'm talking about the fully dense parts. So if you have layer is looking like this, nothing complicated, you can go for this part. But if in some portion the layer looks like this complex, so you can go for this matte process. Or if your layer is too much complicated, you can do this Hilbert geometry as well, or this continuous hybrid geometry as well. So you can choose different contour feeling for different layers to have accuracy in each portion of the part, because different portion of the part may have different curvature, different boundaries, different shape, geometry, topology. So depending upon that, you can change the area filling method. And this is what was covered in the first lecture. If you have any doubt, you can ask me.
And for 3D surface, is there any advantage over the other?
Can you repeat your question?
Like, is there some anything specific to know about 3D surface?
Okay, no, actually 3D surface is a little bit different. So, for example, if you are printing using a robotic arm, and your robotic arm will obviously have more than 3 or 4 degrees of freedom. So, if your robotic arm can move like this, so that will have a 3D layer. Generally, this finger is my tool from which the material is coming, and this is my bill plate. Normally, the printing will take place like this: one layer, second layer, third layer, fourth layer, like that. But if your tool is mounted in a robotic arm which has more degrees of freedom, then even your layer may look like this 3D surface. It has some X, Y, Z, all the coordinates. So in that case, the area filling method will be same like contour, or Hilbert is not that much used. So contour scanning, raster scanning, zigzag patterns, these are the patterns normally used. So in that case, you can just do like this for 3D surface. This is what is meant by 3D surface scanning. Understood?
Yes.
So this gaps, this line, the gap between two tracks, these are important when you're filling the curved surface, because for a flat surface it's same, but for curved surface it will be different depending upon the radius of the curvature. This is all about the first lecture. In the second lecture, professor has covered a few softwares. So it's very interesting software. I don't have all the softwares with me. I use different softwares for slicing and build job preparation. So the softwares are mainly used to define the tool path, define the slicing, put the process parameter for the process, or the simulation of the part, how it will be printed. So these are the things you can see from the software. Next is uh, the liquid aim process. So these are the two liquid aim process that sir has covered. So in this week lecture, sir has covered mostly the VAT photopolymerization technique. So basically, I have already told it in my last to last class how VAT photopolymerization works. It's basically there will be photo initiator, and if you put the UV laser, the photo initiators uh, will give some free radical in the liquid region, in the liquid medium, and that free radical will start the chain reaction in the monomers, and the chain propagates and makes the polymers out of it. And when the polymers is made by the chain propagation, basically it's cured. So you will get the solidified part. I'm not going into deep. Rather, let's go to the previous year questions from week 3. So I'll show the question, you try to answer. In a DD process, a complex shape needs to be filled with very low voids and good boundary retention. Which tool path is preferred? Any guesses? It's matte. Because in matte, see the options. So it's complex shape. So with low voids. So in matte, it will have different contours and different scanning spirals in different regions. So it will be better. It will give better accuracy in terms of the boundary and the voids or porosity. In the zigzag tool strategy, the tool path direction is rotated by an angle in each slice. If grid cutting is applied on the inside of the exterior contour and outside of the interior contour, then so the final area will exclude the desired area. Tool lift is minimum in direction parallel toolpath.
Ma'am, second question, can you show once more?
In the zigzag toolpath strategy, homogenization of the part property could be achieved. So as I said, it will be zigzag and it will be XY asterisk at the same time. Then it will get the homogenization, means the isotropic property of the part. As I showed, na, in zigzag, it will be like this. This is my first layer. So my next layer will be this. I am doing zigzag and I'm rotating the part as well. Then only I will get the homogenization of the layer. Otherwise, I will not get.
Okay.
So this will be the case. If grid cutting is applied, these are straightforward questions. So if you see the PPT, you will get the answers. And if you just watch the videos carefully, you'll get the answers. The spiral toolpath fails in which of the following aspects? Constant step over. The disadvantage of space filling toolpath is lower adaptability with complex geometry. So why it's advantage and disadvantage at the same time, because for complex geometries it's good, but again if it's very complex, then spiral can be a little bit difficult to accommodate in a small place. If you have a very small region to cover, then their spiral will be a little bit difficult to accommodate in that small region. That's why. In which tool path a series of offsets from the outer boundary progresses towards the center? Contour parallel, contour path. In both the cases, if it's contour parallel, means just contour with the parallel lines, and contour path means the whole, it's again parallel, because even if your geometry is having curved surfaces, it will just have the contour and it will reduce the size of the contour till it reaches the center. In the wet photopolymerization process, the method uses to scan the area inside slicing contour is pixel भी use होता है and we use mask as well. In Inkscape, following extensions is used to convert the path to G code. So it, you'll know it if you see the video of the software, how to use it. Which one of the following options in Ultimaker Pura is modified to produce only stale support placement? In power meal adaptive slicing can be enabled. In Ultimaker Cura, if the support overhang is set at 90 degree, then no support will be generated. Support overhang is 90 degree means this is the part. And if it's 90 degree, obviously no support will be generated. If the
Only if
galvanometer
it is
is
only if it is more than 120, it is rendered, right?
yeah. If the galvanometer is combined with floodlight, the wind direction should be none of the above. Again, it's with the video, with the VAT photopolymerization video, you will see how it works. So galvanometer is a tool where it will have multiple mirrors and how the mirror reflects the UV light reaches the resin. It's a bunch of mirrors, so I can't show you here because I don't have any picture of it. So sir has demonstrated how the mirror works. So you will see. The scanning system used by robotic SLA is flying optics. The photopolymer VAT is non-stationary if the scanning system is none of the above. So the photopolymer VAT is non-stationary means flying optics, obviously the VAT is full of resin and it's stationary. Galvanometer, the UV light is reaching and that means the VAT is there and it's stationary and it's having the resin filled in it. So if it's non-stationary, that means it's the process by which the tool itself is carrying the resin and it's drop by drop, it's placing the resin on the bill plate. The purpose of the power prime tower in Ultimaker Cura is again software based. So you have to just see the software video, ensure material extrusion availability for both the build plate material and the support material. So what we can do is you can just note down this question answer so that when you see the video, you can just have a recap with the question answer and the video. If it's matching or if it's not matching, you just can just mail me. In which of the scanning systems mirrors are employed? In galvanometer, it works with the mirror arrangement in X and Y direction. And DLP is again, the screen is there, the mirror is there to deflect the laser or UV light. So all of them. The most unique fact about liquid is can realize transparent object because you are using liquid resin. So it depends what is the color of the resin. If your resin is transparent, then you can print even transparent jobs. If your resin is different colors, then your part will be of different colors. The floodlight source is stationary. In DLP, the UV light comes from bottom, so it's stationary. Mask, again, you're putting the mask for each layer and the light is stationary. The light is coming and falling on the whole bill plate, and wherever the mask is not present, that resin will be cured. And in the galvanometer, again, the galvanometer will have the arrangement of mirrors in the X and Y direction. And the mirrors will just deflect in an angle in such a way that required amount of UV light will be reflected and reach the bill plate. So the UV light is stationary. Flying optics means the UV light is moving on the bill plate and curing the part. The percentage of material saved when a hemisphere of 10 millimeter diameter is built with 30% infill density, 70%. Because infill density 13% means the same. If you are printing a cube with honeycomb structure with 30% infill, means there is 30% material present inside the part and 70% is void. That's all about the previous year question. Now I have a you only have two people. I don't know if both of you will attend or not because this week's lecture videos were pretty simple. I think that is the reason why people are not attending. I have a fun game for you. So if you have a mobile phone, then take it out. You have to scan this QR. Sorry. You have to scan this QR or go to Menti www.menti.com and put this code. You will enter in you will be entered in a live MCQ test. It's an MCQ test on VAT photopolymerization. The questions are pretty simple. Few questions are difficult. So it's just to test how much you have learned. So try to join. This is the code. You can say it's a fun game. This is the QR or this is the code. So you can just put the code in your phone and you can play the game. I think one of you have joined. So other one can join as well if you are listening. No worries, you can join in between as well. So
I'm
let
actually, is it like part of the
no,
third
it's
week lesson?
not the part of the any evaluation. It's from my side.
Because I'm yet to
It's
go
just
through the lecture of week 3.
yeah, it's okay. It's fine. You can put wrong answer if you don't know. There is no nothing. It's just a fun game. When a lot of people join, it's just it will give you bonus points here, but it's nothing related to your course that this points will or this marks will not affect your final grade. So one by one, the questions will come. So it will have 22 seconds to answer. So you have to answer it quickly. VAT photopolymerization in 3D printing works by it's okay even if you put wrong answers. And you will get some points as well. So it's fun when a lot of people join. So the next question is the z-axis resolution in VAT photopolymerization is primarily determined by fast. Okay. So build platform speed means how much the speed at how much speed the build platform is moving up. Remember, when the build platform is moving up, the deposition is not even taking place. It just moves up so that another layer of the resin can come on the top of the previously built part. So it's nothing related to the deposition. It just moves up in such a way that the process will be stable. There will be no vibration in the system. So the build platform will not move up very quickly or very slowly. So it will have it if it's very slow, then it will have more time. So your time is wasted and time is equal to cost. And if it's very fast, then it can produce some vibration in your system. So it should have an optimized time to move up or move down, depending upon which process you're printing with. And uh, at the time of moving up and down, the deposition is not taking place. So the resolution of the part will not have any direct relation with this. But the layer thickness tastings is something like you can put the layer thickness as 100 micron or 50 micron. Depending upon that, your resolution of the part will come. If your layer thickness is very, very small, your resolution will be very, very high, but your time will be very high and cost will be very high because the time is more. But if your layer thickness is very, very more, like your layer is very thick, then your time will be less, cost will be less, but you have to compromise a little bit with the accuracy of the part. Like your layers may be or will be visible even after printing, which is not generally there in wet polymerization technique. So that is the
So,
answer.
so if the layer is big, that means the pixel size will be less, is it?
Okay, so now there is no relation between the pixel size and the layer thickness because pixels are constant. The screen you're putting below the VAT is there for the whole life of the printer, and the screen will have a definite number of pixels which will not be altered, which can never be altered. So it works like your mobile phone. Your mobile camera will have some pixels, your screen will have some pixels, and your mobile camera will have some uh what is the resolution, the quality. And you cannot alter the quality of the phone camera once it's bought, right? It works similarly. So it's nothing related to the layer height. Pixel is giving you lateral resolution. Layer height is giving you the longitudinal resolution. You understand? Is it
Okay.
okay? Okay.
Okay. Okay.
Let's go to the next question. Which of these is a limitation of this process? Easy, easy. Try to recall what are the words related to wet photopolymerization. Yes. So it's photopolymerization. So only photopolymers will be used. Next. The primary post-processing step for wet photopolymerization parts is post-processing means after printing. So generally, always the post-processing will include this UV curing to fully harden the resin. It will just increase the hardness. Next, let's go to the next question. So the right answer is it projects an entire layer image at once. Next question. Can you tell me what do you mean by this entire layer image?
I don't know exactly, ma'am.
Okay, so the entire layer image means what I have shown by the pixel. So in DLP, if the system is pixel-based system, that means the pixels will be activated only on that region where the part needs to be printed. So in that screen, only those pictures will be activated. So it will look like the image of the part to be printed or that specific layer to be printed. Okay,
On the grid.
only grade or pixels.
Yeah.
The pixels will be activated, the layer pixels, where the layer needs to be printed. So it's basically the image of the layer, of that specific layer. So next question, let's see. So which factor most affects the curing depth in wet photopolymerization? So laser power and exposure time, because its curing depth means the layer thickness. So if your layer thickness is, for example, T1, and the curing will take place by either UV or the laser only. So that means the curing depth means how much depth the laser or the UV can penetrate to cure it. So it will be depending upon the laser or the UV parameter. So then the parameter related to laser and UV. So now we have to see which are the parameters. So there is only two parameters. One is the laser power, another one is the exposure time. These are the only two parameters possible to alter in case of the heat source of the vat photopolymerization. So that's why the curing depth means how much layer thickness I should put. So the layer thickness is directly uh, related to the laser power and exposure time. So these two parameters are uh, interdependent. So they are dependent on each other. So you have to see the layer thickness and then you have to define the laser power and the exposure time. So it works like that.
So curing depth and thickness, are they both same, ma'am?
Curing depth and layer. So okay, for example, if your laser power is 20 watt and your exposure time is 2 seconds, and there is a formula. So by the formula, if you see that 20-watt laser power and 2 seconds of exposure time, so the overall energy density is sufficient to cure 20 micron depth of resin, then you have to put 20 micron as the layer thickness. Understood?
Yes.
You can put 20 micron layer thickness or 18 micron or 16 micron, not less than that, and never more than 20 micron. Then the layer will not be cured. So this is the relation. So let's go to the next question. Again, in SLA printing, the laser typically cures the resin layer by layer, point by point. point by point, because in SLA also there can be this screen and this pixel thing. By heating the resin to melting, okay. So resin is already melted. It's in liquid form. So that there was a tricky question. This was a tricky question. So you cannot heat a liquid to its melting point because it's already melted. Like it's already in liquid state. So that's why it's just layer by layer and point by point. It could be like heat the resin to its curing point. Maybe you have missed it. Okay, next question. If the laser scan speed is doubled while maintaining the same power, the curing depth will. So if the laser scan speed is doubled, maintaining the same power. So now just think, when your laser is stationary, you have only two laser parameters. One is power, another one is exposure time. But when your laser is moving, like it's mounted on a flying optics, and the whole head is moving, so the laser is moving, then it will have the laser power and the scan speed, like how fast the laser is moving from one point to another. If the scan speed is high, then for a particular given area, the laser energy density is low. Laser power is one thing, and laser spot diameter is second thing. And energy density means a power divided by area. So how much power you are giving at one point. At the same time, exposure time is also there. So for how much speed, for how much time you are putting that much power, that is also important. So that will give you the heat content of that particular area. So if you are moving the laser very fast onto the build plate, then for a given area, you're not putting enough energy. You're not putting enough heat content. The curing depth is again depending upon how much heat you are giving. So if your scanning speed, you're increasing the scanning speed, means your heat is less for that area. So that means it will not reach the full penetration depth. It will not reach the full penetration depth. So that means it will not reach the full penetration depth. So that will give you the heat content. Sorry, my connection was lost again. I think there is some problem with the network today. Are you there?
Yes, ma'am.
Okay, sorry. So, what I was saying, if you are increasing the scan speed, that means you're putting less energy density for a given area. So that may not be sufficient to cure that much depth or that much thickness of the resin. So that's why if your scanning speed increases, then the curing depth will decrease. Now there is a relation, so it's logarithmically decreasing. That is the point. Next question. Now why it is slow. Four more questions to go. Shrinkage stress in cured SLA part is mainly caused by. So it's a tricky question. Just try to think about the process, what I have said. Yes, so cross-linking density changes the volumetric contraction during cure. Shrinkage stress means when you are curing the SLA part, so obviously it's going from liquid state to a solid state, and it's also getting hardened. It's
Ma'am,
also
one doubt
getting densified.
is,
Yeah.
does this laser scanning help in curing?
Okay, so I have demonstrated the stationary optics one. There is one process in which people use flying optics, which means your laser is moving from one point to another point. In the DLP process, the UV light is not moving. It's there. It's exposed for 4 seconds or 3 seconds for a layer. So it's not moving. So it will have a power and the exposure time. But if your laser is moving from one point to another point, just imagine how you can just move a laser pointer from one point to another point. Just like that, the laser is moving from one point to another point onto the resin, and from whatever path it is moving, that area is getting cured. Then your scan speed is actually the exposure time that you are giving for a given area. Understood?
Okay, so based on how much time we are putting the laser on that particular area, the
Yes.
curing will take place, right?
Yes, yes. Based on
Okay.
how much time and how much power we are putting.
Okay.
So
If
in
the
case of
power,
stationary,
uh,
yeah, yes.
so if the power is more, what will happen, ma'am?
So
Laser
if the
power.
power is more, it's not about more or less. As I said, it's like the how much power for how much time you are putting for stationary laser. So that combination, if it's enough to cure 20 micron depth of resin, then you can choose the layer thickness as 20 micron. So if your power is 20 watt and 3 seconds of exposure time is enough, then your power is 20 watt. Now, if you're putting less than 20 watt, then that much depth will not be cured because that much heat is not coming. Laser power is directly proportional to the heat. Power is basically heat. So if we are putting less power, less than 20 watt, the curing depth will decrease. That much resin will not be cured. If you are increasing the laser, then you are putting overexposure, like more power than what is required. So two things can happen. One is a lot of polymerization will take place. So over polymerization, it will harden a lot. And if your laser power is very, very high, for example, 20 watt was needed, and you have put 100 watt, then you may burn the resin. So resin is a thermoplastic polymer. It will not get melted after saltification. It will get burned. So these are the two possibilities that can happen. Okay.
Okay. So here
So who?
the answer,
Yes.
the shrinkage stress in cured SLA parts is caused by cross-linking density changes and volumetric contraction during cure.
Yes.
That means shrinkage means during curing it will get shrinked, is it? Or,
Yes, because
ah,
that's what I was explaining. So,
ah,
just a second. Whoever
ah,
else has joined the meeting, you can go to www.menti.com and use this code to join this PPT, this MCQ question. It's just a fun game. It's nothing related to your points for the exam. It's just to revise your concept. Okay. So, in case of wet photopolymerization, when you're curing the resin, it's going from liquid state to solid state. So obviously
yes,
there will be some shrinkage,
yes.
and because of the shrinkage, and also the shrinkage is taking place in the presence of heat. So there is heat, there is shrinkage. So there will be some stress developed, and the stress is mainly coming from the cross-linking density changes, because of the cross-linking, the curing taking place, so the density is getting increased. Basically, it's getting dense because it's solid now. Volumetric contraction during curing, obviously, because again, it's going from liquid to solid. So volumetric contraction. So both this point agrees with the
Ma'am,
shrinkage.
one doubt is that, but
Yes.
during shrinkage, if the heat is coming up, how can it change from liquid to solid? Usually, if
Because
the heat is coming up,
yeah,
usually solid will change to liquid only, right?
yeah, but it's a photocurable resin. You are talking about metals. You are talking
Yeah.
about maybe ice. When you put the energy, it gets melted. But it's reverse because it's a monomer which is present. When you put the heat, it's a polymerization taking place, means at the presence of heat, at the presence of light, the monomers will start connected with each other and it will make the polymers, which will again make the solidification. So it's different process. That is different material. That is the normal material like metals. Here, the material itself is different. It's a liquid resin, which is a photopolymer. And photopolymer means the polymer which gets cured in the presence of light, which is photo. So that's why it's different. The material itself is different. It works like that.
Okay.
Okay. Yes. So next, you can join or you can just see how the test is going on. So the next question is, which parameter would you adjust to increase the lateral resolution in DLP printing without changing resin chemistry? So there are few things to note down here. First of all is when you are talking about DLP or any VAT photopolymerization technique, you are using the photopolymerization, which means if you're using a resin that is having a one wavelength photopolymerization only, means if you're taking 532 nanometer curable resin, that means the resin will be cured only if you are putting a light with 532 nanometer, which is a green light. So it's better to put the laser because laser will only have 532 nanometer and it will not have any other wavelength. But the sunlight or the normal light, daylight has all the various 400 to 700 nanometer wavelength. So that's why if it's 232 nanometer curable resin, that means it needs a UV light to cure. And if you change the wavelength of the light itself, the resin will not be cured. So that is its property. It will only extra. It will only give the free radicals when it's exposed to 232 nanometer UV light. If it's a 232 nanometer UV light curable resin. So in the packaging itself, it will be written that which resin it is. So the third option, which is a use a higher wavelength light source, it's not valid. Now, for example, even
So
if
even
you,
sunlight is having 400 to 700 only, is it? So
yeah,
okay.
no, sunlight is having all wavelength. It has UV light, it has more than 700, it has less than 400. But I'm talking about the white light. So the white light is having 400 to 700 nanometer, which you can see in the sunlight. There is UV radiation, UV exposure also, na? Because of the hole in the ozone layer. So UV light is also there a little bit, which damages our skin. So this is the thing. So another thing is, if you're taking a resin which is having the curability in a range of wavelength. For example, you have taken a resin which can be cured in between 400 to 500 nanometers. This is the property of the resin. It depends upon the property of the resin. It differs from resin to resin. So now, if you change the wavelength, you change the absorptivity of the light in the resin. So the resin will change its absorptivity. So its absorptivity at 400 nanometer will be different than the 500 nanometer. So it may absorb more or less. So it's typically it will absorb more in 400 nanometer because absorptivity is more when the wavelength is less. That is the relationship we have. So now in that case, if you are using a higher wavelength light source, you will change, you will end up changing the absorptivity of the laser in the resin, which will change the chemistry of the resin photopolymerization. So if you read the question carefully, it's increase the lateral resolution in DLP without changing the resin chemistry. So this is why this option is not valid here. Now increase the resin viscosity. Again, the viscosity comes with the temperature. So if you are changing the light source, like if you're changing the laser power, you can change the viscosity. But if you're changing the viscosity, you will end up changing the chemistry. So if you reduce the pixel size, then only you can change the resolution. So I have told you from the first question itself that if you reduce the pixel size, you can change, you can increase the lateral resolution of the process. If you decrease the layer thickness, you will increase the longitudinal resolution of the process. Understood?
Yes.
Okay. So let's go to next question. So it's the second last question. Post curing under UV light improves. I think it's not covered in the lecture yet, but I have mentioned it today. It does not increase the flexibility of the part. It does not decrease the density, but it increases the density and it increases the hardness. So the thermal stability and degree of conversion of the polymer network. So basically, the degree of conversion means the polymer network will expand, so the hardness and the density increases. Next, the last question. The optimal laser wavelength for most SLA photopolymers in the UV range, because UV photons match the absorption spectrum of common photo emitters, as I've explained. So, correct. So, that's the end of the test.
Ma'am, one doubt is actually
Yes,
reducing pixel size, will it reduce the lateral resolution? Is it like that?
yes,
Oh.
yes.
Similarly, layer thickness also, if it is reduced, it will reduce the longitudinal resolution. Is it
No, if you reduce the layer thickness, you will increase the resolution of the longitudinal
longitudinal?
resolution.
Okay, okay.
Yes,
But
like the Z.
reducing pixel size will reduce the lateral resolution.
No, increase, increase.
Oh, in both case, it is inversely proportional.
Yeah, yeah. Both cases. If you just if you see this slide, no, you just try to recall this slide. If you reduce the size of the pixel, you will end up covering the part smoother
Yes.
in a better way. The accuracy of the periphery will be better. So
Okay.
that's why if you reduce it, you will increase the resolution. Okay.
Okay.
Okay. So let's end the class here. Thank you for attending. If you have more doubt, you can contact me via mail.
Okay, ma'am. Thank you.